Welcome back. In our mini lectures last week, we talked about the electromagnetic spectrum, some of the properties of light, especially the wave properties of light, and we talked about black body spectra. This week we're going to delve even further into what light can tell us, and we're going to begin by talking about spectra in more detail. And in particular, in this mini lecture, we are going to cover spectral lines, both where they come from and what they can tell us. First, we need some definitions. A spectrum is some representation of the intensity of different wavelengths of light from an object. So, for example, this can be a picture of a rainbow where we see brighter colors where there's more light coming, fainter where there's less light coming. It can be a graph. We talked about how we graph spectra last week. We'll review that this week. And typically we use a graph and we plot on the x-axis wavelength or frequency or energy of the light, and on the y-axis we will plot intensity of the light. A spectroscope is any instrument that splits light into a spectrum. The simplest type of spectroscope is a prism, which is just a piece of glass that light passes through and splits up into different colors. However, they can become very complicated on some of the large astronomical telescopes that we have today. And finally, the last related word is spectroscopy, or sometimes called spectrometry. Both of those mean the same thing. It's the study of the spectra of objects in space and what that can tell us about the objects. Spectroscopy really began under Sir Isaac Newton. One of the many things he was known for, in addition to gravity and his laws of motion, was his exploration of optics. It was Isaac Newton who first understood how a prism can split light into component colors, and that white light consisted of a combination of many different wavelengths of light. So here's a picture of him in his study on the left. If you're having trouble seeing that image, here's a slightly more detailed image. And basically Newton blocked off most of the light coming into his room except for a small stream between some holes in a board, and he put a prism up to that and saw the component colors that came out on a screen. So here are some examples of spectra that you may have seen before. In the top left is a double rainbow. On the right is a representation of a prism from Pink Floyd's Dark Side of the Moon. In the middle is an actual picture of a stellar spectrum, and you see not only are there colors there, but there are some dark lines that we will have to explain. And underneath is a graph of that same spectrum showing how there are dips in the intensity of light corresponding to those dark lines. So let's talk about the three types of spectra that are most commonly seen in astronomy. The first, which we've actually already talked about, is called a continuous spectrum. A continuous spectrum is any spectrum that spans large regions of wavelength without interruption. And this is the type of spectrum that we get from a black body, though there are other ways to make continuous spectra. But here's a good example. We have an incandescent light bulb, which is glowing because it's hot. The light goes through a prism, gets spread out into its component colors, and we see all the colors from blue through yellow through red. And then we can plot this spectrum with wavelength on the x-axis. In this particular representation, red, longer wavelength, is to the right, and intensity on the y-axis. And for this light bulb, the graph tells us that most of the light is coming out in the reddish orange, with less as you go to the blue and less as you go to the infrared. Another type of spectrum is an emission line spectrum. An emission line spectrum is caused when you have a cloud of gas that has been excited somehow. Maybe it has had a collision, maybe it's very hot, maybe we are pumping electricity into it. And this emits light. When we split the light up into its component colors, we see that most of the spectrum is dark, with these very bright lines at specific colors, such as here, or here, or here. And on the plot, we would see that as black at most wavelengths, no light whatsoever, and then very narrow spikes at these emission lines. The wavelengths that come out depend on both the composition of the gas and the temperature of the gas. So if we see one of these, we can not only figure out what the cloud is made out of, but what gases are there, but also what temperature it is. A very common example of emission line spectra that occur in everyday life are neon lights. Neon lights put out a lot of emission lines in the orange and red, and the way that a neon light works is that we pump electricity through a tube that's full of nothing but neon gas. And so what we get out are the colors, the emission lines from excited neon. Each element has its own emission line spectrum. So if we look down, here is neon, and you see that neon has a lot of emission lines in the red and orange and into the yellow, which is why a true neon lamp looks orangish in color. Some other common elements, hydrogen, the most common element in the universe, has a bright red line, a aqua colored line, a blue line, and then several lines in the violet. Sodium gas, which we talked is a very common type of streetlight, puts out only two emission lines close to each other in the yellow. And this is why sodium lamps look sort of an orangish yellow color, because that's the wavelength corresponding to these two lines. Helium has several lines of different colors, mercury has several lines of different colors, and what you notice is that although some lines look like they are similar colors, no two of these elements have lines at exactly the same wavelengths. So if we can determine what lines are present, we can determine what elements are present. It's very much like a fingerprint. The final type of spectrum we will talk about is an absorption line spectrum. Here on the right you can see a typical absorption line spectrum. It looks almost like a continuous spectrum, except there are these dark lines superimposed at very specific wavelengths. At these wavelengths there's much less light coming out than at most wavelengths. The way that we get an absorption line spectrum is we start with a hot, dense source like a black body, here an incandescent light bulb. The light from that source passes through a cloud of gas, and this can be any type of gas as long as it's not too hot. And then when we look at that light, we see these dark lines. To create these lines, the gas must meet certain criteria of temperature and density. A curious fact, or at least curious for now, is that these dark lines appear at exactly the same wavelengths that bright lines would appear if all we could see were the cloud of gas being energized from within. So if you have light from a black body passing through a cooler gas, then you can often end up with absorption lines. The sun provides an example of all three types of this spectrum. Here's a diagram of the sun. Let's not worry about most of the sun yet. We will talk about the sun in a couple of weeks. But the important part of the sun for our purposes is the photosphere. The photosphere is the top layer of the sun, and we often can think of it like the surface of the sun. And the photosphere of the sun is a very hot, very dense plasma. And so you would expect that it should produce a continuous spectrum, and in fact it does. Above the photosphere is another part of the sun called the chromosphere. The chromosphere is like the atmosphere of the sun. It's a thin gas that sits above the photosphere. Because it is so thin, we can only see it during a total solar eclipse when the photosphere of the sun is blocked out by the moon. The chromosphere is energized by magnetic fields, by solar flares, and by the sun's surface. And if we look at the spectrum of the chromosphere during a total eclipse of the sun, we see an emission line spectrum. Here is a spectrum of the sun's chromosphere taken during an eclipse. The lines are curved because the edge of the sun is curved, and that's the only part of the chromosphere we can see. And you see that there are very specific wavelengths at which light is coming out, and if we were to look closely we would find that these correspond to some very common elements like hydrogen and sodium. So here's a plot of that spectrum, and underneath the same spectrum but straightened out. So this is the solar chromosphere seen during an eclipse, and what we see are lines, emission lines from hydrogen, from helium, from sodium, from magnesium, and from iron and calcium. There are actually many other lines in here. Much of this stuff that looks like a continuous spectrum is actually individual emission lines that are all running together. If we take a spectrum of the sun when it's not in an eclipse, we see an absorption line spectrum. And that's because the continuous spectrum from the photosphere passes through the thinner gas of the chromosphere on its way to us, and the gas in the chromosphere absorbs light at the frequencies corresponding to the gas that's there. So this is an absorption line spectrum of the sun. The dark lines in the solar spectrum were first noticed by an astronomer named Fraunhofer, and so they're often called the Fraunhofer lines, and he didn't know where these lines came from, so he just gave them letters. If we compare this absorption line spectrum of the sun to the emission line spectrum of the chromosphere, we see that most of the lines match up. That this line in the red, which we said was hydrogen, matches with an absorption line in the red. This that we said was both sodium and helium matches with this D line in the yellow of the sun spectrum. So notice that the emission lines in the chromosphere match exactly with the absorption lines seen in the light coming from the photosphere. I will now show you some example spectra. On this slide we have the spectra of 3 different stars. The sun, which obviously is our home star, the star Algol, which is visible in the fall sky in the constellation Perseus, and the star T Tauri, which is a star in the constellation Taurus, visible during the winter. So from the Earth, both Algol and T Tauri just look like typical stars, points of light. But if we compare their spectrum to that of the sun, we see that they are very different. First of all, Algol has many fewer absorption lines than the sun does, and the absorption lines that we see in Algol match up with hydrogen, and you can see that those colors that are there do match with colors in the sun. Also, Algol has a much more intense blue and violet light coming from it, and much less intense red light than the sun. This is because Algol is a very hot star, and so its spectrum peaks in the violet and in fact in the ultraviolet. Finally, let's go to T Tauri. T Tauri is a yellowish star like the sun, and you can see a continuous spectrum that more or less peaks in the yellowish green part of the spectrum. But instead of dark absorption lines in T Tauri, we see bright emission lines, and this tells us that near the star there must be some energized gas that is emitting light at specific wavelengths, and these wavelengths correspond to hydrogen. T Tauri is a star that is in the process of forming, so it's got a hot object at the center that produces the continuous emission. That object will become a star one day, but gas is still falling onto the star from far away. As it falls in, it gets excited, it gets energized, it runs into each other and creates these emission lines. So whereas to our eye, Algol and T Tauri would just look like normal stars, we see that in fact they are vastly different from a star like our sun. Let's now look at some examples of spectra of objects in our solar system. The sun is the only object in our solar system that produces its own visible light. All other objects in the solar system shine because light comes from the sun, bounces off the object, and comes back to the Earth. And if that object has an atmosphere, then this light from the sun passes through the atmosphere of the planet or moon and then comes back to Earth. So at the top we see the spectrum of the sun. If the planets were perfect mirrors, this is the type of spectrum we should see. But if you look at the spectrum of Titan, you will see this sort of dark area in the reddish orange. It's just a very light absorption feature, but it's not there in the sun. This is due to methane. Methane is a very common molecule in the atmosphere of Titan, and so we would expect that this methane should absorb light at specific wavelengths as it passes through Titan's atmosphere. The bottom spectrum is a spectrum of the planet Uranus. In the spectrum of Uranus, you see many dark absorption features, all of which correspond to methane. Uranus has a methane atmosphere like Titan, but it's much thicker, and the sunlight goes deep into the atmosphere before reflecting off and bouncing back to us on the Earth. By looking at the spectrum, you can tell why the planet Uranus and Neptune, which is very similar, look a bluish-green color through a telescope. The reason is that much of the yellow, orange, and red light coming from the sun is absorbed by the planet's atmosphere. However, the planet reflects the aqua and green and blue and violet light, and so to our eyes the planet looks a bluish green color. So let's summarize what we know. A spectrum is a plot of the amount of light or intensity of light detected as a function of wavelength, or we could also plot frequency or energy, since we know from last week that these are related to wavelength. The main types of spectra are a continuous spectrum, which shows all wavelengths of light, an emission line spectrum, which is mostly dark with bright lines at very specific wavelengths, and an absorption line spectrum, which is like a continuous spectrum except there are dark lines at very specific wavelengths. I expect you to know the types of conditions that produce each type of spectrum. A continuous spectrum can come from a black body. An emission line spectrum comes from energized gas, and an absorption spectrum comes when light from a black body passes through gas on its way to us. In the next mini lecture, we will discuss exactly where these lines come from, why they occur at specific wavelengths, and why we can use these to tell what elements are present in a star.